Imagine the center of our galaxy as a busy, crowded city square. Stars zip past each other, gas clouds pile up, and the traffic patterns, the ways things move and where they end up, are shaped by a big, invisible force right in the middle. That force is Sagittarius A, the supermassive black hole that sits at the heart of the Milky Way. It's not a roaming monster gobbling stars. It's more like a massive anchor and occasional fire hydrant. It keeps the neighborhood organized, and every now and then it sprays out energy that reshapes the environment for thousands of light years. To get a feel for how important that anchor is, let's zoom in and out, look at what SGRA does locally, how it interacts with the whole galaxy, and how those interactions ripple outward to affect the conditions that ultimately made planets like Earth and life possible. First, what is Sagittarius A? It's a region only about as big across as our solar system, but with a mass equal to roughly 4 million suns. Most of the galaxy's gravity comes from stars and dark matter spread across tens of thousands of light years. Yet the black hole's gravitational pull is dominant in the very center, roughly the inner few light years. And we can see its influence clearly because stars near the core orbit extremely quickly and tightly. Watching these stars is how astronomers proved there's a massive compact object there. A star named Estwo, for instance, swings around Sagittarius A every 16 years on a very tight orbit, getting as close as 17 light-hours to the center. Those precise orbits, tracked over decades, left only one plausible explanation: a very compact mass, too dense to be anything but a black hole. This work earned the Nobel Prize in Physics in 2020, and it's one of the cleanest pieces of evidence we have that supermassive black holes truly sit in galactic centers. Now you might ask, if that black hole is so heavy, why don't we see it tearing everything apart? The short answer is distance and quiet behavior. Sagittarius A is relatively calm compared with the bright, active black holes at the centers of some other galaxies. Right now it's in a low-feeding state. It swallows only tiny amounts of gas, which makes it dim in most wavelengths. That calmness combined with the fact that we're about 26,000 light-years away from the center means we are safe from any direct effects. Even when the black hole flares, the energy is spread over such a large volume of space that life on Earth feels nothing. But calm doesn't mean unimportant. The black hole's presence has shaped the Milky Way's history in ways that are indirect but profound. Think about two kinds of influence: gravitational and energetic. Gravitationally, Sagittarius A sets the orbital stage in the central region. The stars that orbit close to the center, a group known as the S-stars, move under its gravity. Their orbits allow astronomers to measure the black hole's mass and to study how gravity behaves in extreme conditions. But the black hole's gravity is dominant only in the inner parsec or so. A parsec is about 3.26 light-years. Outside that, the galaxy's stars and dark matter take over. So the gravitational effect is locally dramatic but globally modest. However, the energetic influence, the radiation and mechanical outflows the black hole has produced over cosmic time, can travel far beyond that small radius and alter the galaxy's gas and star formation across thousands of light-years. When a black hole actively feeds, when it draws in a substantial amount of gas, that gas forms a swirling disk around it. Infalling matter heats up, shines brightly, and can launch powerful jets and winds. Those active galactic nuclei, AGN, are among the most luminous phenomena in the universe. In many galaxies, the central black hole went through active phases early in their history and injected vast amounts of energy into their surroundings. That energy can heat and push away gas that would otherwise cool and collapse to form new stars. The result is a kind of galaxy-level thermostat. Black hole activity can limit excessive star formation, especially in the most massive galaxies, and help determine whether a galaxy becomes a bustling, blue star factory or a quieter, redder place. This regulation is called feedback, and it's a central idea in how astronomers think galaxies and black holes grow together. Our Milky Way's black hole does not currently dominate the galaxy's star formation, but evidence shows it wasn't always so quiet. The galaxy bears scars of past activity. A striking example is the pair of giant gamma-ray lobes that extend above and below the galactic plane, known as the Fermi bubbles. These structures were discovered in 2010 and span more than 25,000 light-years from end to end. They look like two giant balloons coming out of the center of the galaxy. Their shape and energy suggest that the core of the Milky Way experienced a significant release of energy a few million years ago. Perhaps either a period of increased feeding by Sagittarius A or a burp of star formation and supernova explosions in the central region. Those bubbles pushed and heated gas, and they've likely influenced how gas circulates in the inner galaxy since then. Why does that matter for the galaxy as a whole? Because star formation depends on gas that's cold enough to collapse into dense clouds. When black hole activity heats the gas or blows it away, the supply of cold gas is reduced, and the galaxy slows its rate of producing new stars. Think of it like a garden with a sprinkler. If you flood the soil with hot water, you kill the seedlings. If you install a valve that periodically opens and sprays hot water across the beds, you keep the garden from being overrun. Similarly, feedback from a supermassive black hole can prevent runaway star formation and shape the life cycle of the galaxy. On the other hand, moderate outflows can also compress gas in certain regions, triggering bursts of star formation in localized pockets. So the effect isn't simply suppressive, it's dynamic and complex. Another way Sagittarius A affects the Milky Way is by sculpting the central structure. Many galaxies have a dense region in their centers known as a bulge, and there's a statistical relationship between the mass of a galaxy's central bulge and the mass of its central black hole. This correlation hints that galaxies and their black holes co-evolve, each influencing the growth of the other. In our galaxy, the black hole and the central bulge seem to have grown together, with gas flows into the central regions, feeding both star formation in the bulge and the black hole. Structures like the galactic bar, a long, elongated concentration of stars crossing the Milky Way's center, can channel gas inward. That inward flow can feed central star formation, or, occasionally, the black hole itself. Over cosmic time, these processes help determine the mix of old and new stars in the central regions, the distribution of metals, elements heavier than hydrogen and helium, and the overall shape of the Milky Way's inner parts. Sagittarius A also contributes to the galaxy's dynamics in other interesting ways. When a star ventures too close to a black hole, tidal forces can rip it apart in a violent event called a tidal disruption. The shredded star's gas briefly glows as it spirals into the black hole. These are rare events, but they do occur, and they produce bright flares across many wavelengths. If the Milky Way's black hole were absent, the central region would lose this particular type of fireworks, and the rate of such destructive close encounters would change. The black hole also plays a role in creating hypervelocity stars, stars that are flung out of the galaxy at hundreds or thousands of kilometers per second. One mechanism for producing such speedy runaways involves a binary star system getting too close to the black hole. The intense gravity can capture one star and violently eject the other. The result: a star is slingshotted out of the galaxy. These escaped stars are a peculiar signature of black hole interactions, and without a central black hole, the population and trajectories of high-speed stars would look quite different. You can also follow a more subtle trail from the black hole to the elements on Earth. Stars are the factories that forge the elements heavier than helium. The number, timing, and locations of star-forming episodes determine how the galaxy's chemical mix evolves. Supernovae spread newly made elements into the interstellar medium, enriching the next generations of stars and the planets that form around them. If Sagittarius A had prevented or delayed star formation episodes in the Milky Way's pass-through feedback, it would have indirectly influenced the timing and distribution of heavy elements. That in turn affects when and where rocky planets form and their elemental makeup. So while the black hole isn't directly seeding Earth with elements, its control over gas and star formation has ripple effects that can change the environments where planets and life-friendly chemistry emerge. It's tempting to imagine a binary, with or without scenario, Either the Milky Way had a black hole and life eventually arose, or it had no black hole and life might look different. Reality is more nuanced. Many galaxies host central black holes, and many galaxies without obvious supermassive black holes are rare or hard to study in detail. The presence of a central black hole doesn't guarantee a hospitable environment for life. Many other factors, the galaxy's size, its rate of star formation, its history of mergers, the metallicity of its gas, play important roles. Still, black holes are a major piece of the puzzle because they can modulate those other factors. Thinking about Earth specifically, could Sagittarius A have ever posed a direct threat to life here? No strong evidence suggests so. The black hole is too far away and too quiet for its normal activity to bathe the solar neighborhood in lethal radiation. Even if SGR-A experienced a powerful outburst many millions of years ago, the energy that reached Earth would have been diluted enormously by the time it traveled 26,000 light-years. The Fermi bubbles, for example, are dramatic on galactic scales, but would not have delivered a life-threatening dose of radiation to the inner solar system. That said, a truly extraordinary nearby event, say, an extremely energetic jet pointed exactly at Earth, could, in principle, increase radiation at our planet, but such alignments are unlikely, and the timing would likely be obvious in the geological record. More relevant to life on Earth are local events like nearby supernovae and gamma-ray bursts, which could have direct effects on planetary atmospheres if close enough. Let's imagine the Milky Way with no central black hole. Picture the same spiral arms, the same disk of stars, but the inner city has no massive anchor. What would change? First, the tight cluster of rapidly orbiting S-stars would not be the same because their orbits reflect the gravity of a compact central mass. There might still be a dense nuclear star cluster, but it would be more diffuse, perhaps hosting many compact objects like neutron stars and smaller black holes spread over a larger volume. Without a massive central pull, the dynamics of that region would differ. Stars might collide or merge more frequently because nothing corrals their orbits into the tight, high-speed patterns we observe. Conversely, some inspiral processes might be less common. More broadly, the Milky Way's early evolution could have been different. If there were no supermassive black hole to inject energy at key moments, the central gas could have cooled and formed stars more efficiently, especially during early, active phases when galaxies were assembling. The result might be an overabundance of stars in the central regions, a bloated bulge, or a different bulge-to-disk ratio. In the most extreme models, the absence of black hole feedback could leave galaxies more compact and richly star-forming than we observe today. This discrepancy is in part why astrophysicists include black holes in simulations of galaxy formation. Without them, models often end up with galaxies that are too massive or too blue, too many young stars, compared with the real universe. Another consequence would be a different population of high-speed and runaway stars. If Sagittarius A is not present to perform the dramatic slingshot of binary companions, hypervelocity stars would be rarer or would arise through different mechanisms, such as gravitational interactions during galaxy mergers. Similarly, the frequency and character of tidal disruption flares would change. We might see fewer bright flares from shredded stars, which would alter the high-energy emission history of the galactic center and the ionization state of gas in certain regions. Black holes also play a role in sculpting the distribution of gas at large scales. When a black hole heats gas and drives winds, it can lift material out of the disk and into the halo. This cycling keeps some gas from collapsing immediately, allowing it to mix and cool on longer timescales before raining back down and fueling later generations of star formation. Without that mixing, star formation could proceed in a more bursty, less regulated fashion. Big spikes of star formation followed by long lulls, rather than a more steady supply of new stars. This pattern would influence the types of stars and planetary systems that form, and therefore the chemical environments available for life. A galaxy with much more intense early star formation might drive heavy elements into the interstellar medium sooner, but it could also exhaust its gas reservoir earlier, leaving the galaxy red and dead sooner than otherwise. There are also cosmological angles to consider. Supermassive black holes are linked to the growth of structure in the universe. They likely start as smaller seeds, maybe the remnants of the earliest massive stars or from direct collapse gas clouds, and grow by eating gas and merging with other black holes during galaxy collisions. These growth processes feed back on the host galaxy. Removing black holes from the picture altogether would change how galaxies evolve over cosmic time and could lead to a different distribution of galaxy types in the universe. The observed correlations between black hole mass and the properties of the host galaxy's bulge would not be there to guide the coevolution narrative, and our theoretical understanding of galaxy formation would look very different. On an observational level, the presence of Sagittarius A has been a boon. It's a unique laboratory for testing gravity in the strong field regime, for studying relativistic orbits, and for seeing how matter behaves near an event horizon. The Event Horizon Telescope's image of the shadow of the black hole in the galaxy MADI 7 was a landmark, and later observations of SGR-A's surroundings allow astronomers to compare different black holes and refine models of accretion and outflows. Without a central black hole, we would lose one of the most important natural experiments in extreme gravity, limiting our ability to test theories like general relativity in high-curvature environments. Let's step back and think about scales and probabilities. The fact that most galaxies we can measure do have central supermassive black holes raises the question: are black holes essential for galaxies to look like they do? The answer is tentative but leaning toward yes, in the sense that black holes are a key ingredient in producing the diversity of galaxies we observe. They help regulate star formation, shape central bulges, and interact dynamically with their surroundings. However, this doesn't translate into black holes being essential for life everywhere. Life is a product of many factors: a stable planet, the right chemical ingredients, a star with a long, quiet life, and a stable orbital environment. Many of these requirements are local and depend on the properties of star-forming regions in the disk, rather than on the central black hole. That said, because Sagittarius A influences the overall star formation and chemical enrichment history of the Milky Way, it plays an indirect role in creating the conditions that led to the formation of the Sun and the Earth at the particular time they did. A thought experiment helps make this concrete. Suppose there had been no black hole at all, and the Milky Way's central gas formed stars much quicker early on. That could have enriched the galaxy sooner with heavy elements, potentially allowing rocky planets to form earlier. But if the gas burned through too rapidly, later generations of stars, those forming billions of years after the Big Bang, might be starved, reducing the window for stable, long-lived planetary systems to form. Conversely, if the black hole's feedback was too strong, it might have suppressed star formation so much that heavy elements were rare, making the emergence of rocky planets more difficult. The delicate balance we observe in the Milky Way, enough star formation to build planets, but not so much to exhaust the gas too early, may be at least partly a consequence of the black hole's moderating influence. There's another subtle point to consider: the difference between mass and power. Sagittarius A holds a lot of mass in a very small region, and that's what makes it interesting gravitationally. But when it comes to shaping the galaxy, the important thing isn't just how massive the black hole is, it's how much energy it dumps into its surroundings. A relatively small black hole that eats voraciously for a time can have more impact than a much larger one that remains quiet. That's why some comparatively small galaxies with active nuclei can be dramatically altered by their central engines, while some big black holes like SGR-A can be almost invisible if they're not accreting material. The Milky Way's black hole has likely flickered through different activity states over time, and those flickers have left imprints, from star formation histories to the creation of structures like the Fermi bubbles. We should also consider how the black hole interacts with other compact objects and how that changes the galaxy's central environment. The center of the Milky Way is a crowded place with many stellar remnants, neutron stars, and stellar mass black holes. These objects interact gravitationally with each other and with the supermassive black hole. Over billions of years, some of these compact objects migrate inward via dynamical friction and may merge with the central black hole, producing gravitational waves. Without a supermassive black hole, you'd have fewer extreme mass ratio inspirals, where a small object spirals into a massively larger one, and the gravitational wave sky would be different. For astrophysicists, that matters because such events are valuable probes of strong gravity and black hole astrophysics. Finally, there's an anthropic angle. Could the presence of a central black hole be part of what makes a galaxy conducive to life? That's a tricky question because it mixes science with selection effects. We can only observe life where life exists. Perhaps life arises preferentially in galaxies with certain histories, and maybe central black holes are one ingredient in those histories. But pinning down a direct causal chain from has a black hole to produces life is hard. The safest statement is that black holes are an important piece of the galactic ecosystem. They help regulate star formation, influence chemical enrichment, and shape central dynamics, all of which affect the distribution and timing of environments where planets form. That makes black holes relevant to the broad conditions that govern habitability on galactic scales. There's also a poetic practicality here. Supermassive black holes are one of the most efficient ways to convert mass into energy. When gas falls into a black hole, a surprisingly large fraction of its mass can be converted into light and outflows. That efficiency makes them powerful actors in a galaxy's drama. The energy released by even a modest feeding episode can rival the combined output of millions of stars and can travel vast distances, heating and stirring gas in ways that the relatively more sedate processes of stars alone cannot. So while Sagittarius A doesn't rule the Milky Way by mass, it can punch above its weight in terms of energy output. If you imagine removing the black hole and replacing it with more ordinary mass spread out across the central region, the changes would ripple outward. The central stellar dynamics would shift, the timing and pattern of star formation could be different, fewer tidal disruptions and hypervelocity stars would be produced, and the chemical evolution might follow a different path. On the flip side, some things would remain similar. The spiral arms, much of the disk, the Sun's local neighborhood. Those are largely shaped by larger-scale gravitational structures and the distribution of dark matter. The black hole's absence would not, for instance, cause the spiral structure to vanish overnight. Instead, its absence would nudge the galaxy's long-term evolution toward different outcomes. There's a final practical point worth making. Studying Sagittarius A teaches us about high-energy physics under conditions we cannot replicate on Earth. The region near a black hole is where magnetic fields, relativistic plasmas, and gravity dance together. Observations across the electromagnetic spectrum, from radio waves to gamma rays, let astronomers piece together how energy is extracted from accreting gas and how jets are launched. Without a central black hole, we would lose a natural laboratory for these processes, and our understanding of fundamental physics would be poorer. That's not directly about life on Earth, but it's about how we, as curious observers, understand our universe. So the presence of Sagittarius A in the Milky Way is both subtle and significant. It acts as a local dynamical powerhouse, shaping the orbits of stars in the innermost region. It has been, at times, an energetic engine that injected energy into the galaxy, carving structures like the Fermi bubbles, and influencing how gas flows and cools. Through these influences, it has helped shape the Milky Way's star formation history and chemical evolution, the raw materials and timing that ultimately matter for planet formation and the potential for life. Remove the black hole, and you change the galaxy's evolutionary script in meaningful ways, even if many large-scale structures remain recognizable. The black hole doesn't directly cause life, but it's an important part of the story that led to the conditions under which life as we know it could arise. If we keep following this thread, the next question is how specific changes to black hole properties, like a black hole that's 10 times heavier or one that never actively fed, would alter galactic outcomes in detail. We can also dig deeper into evidence from other galaxies. How do galaxies with different black hole histories compare to the Milky Way in terms of star formation and habitability? And what do simulations tell us about the range of possible galactic futures depending on central black hole behavior? Exploring those lines of inquiry will bring us closer to understanding not just what Sagittarius A has done so far, but what roles black holes play across the universe in shaping the contexts where stars, planets, and potentially life emerge. So where do we go from here? We started by thinking about the Milky Way as a city with a busy central square, Sagittarius A as the anchor that organizes traffic and sometimes sprays energetic jets like a fire hydrant. The natural next step is to look at the different ways a central black hole can behave, and how changing its mass or its diet changes the life of a galaxy. Along the way, it's useful to clear up a small side topic that keeps popping up when people talk about removing a black hole or turning it off. The word undefined. It sounds technical, but the idea is simple and it helps keep our reasoning straight. In everyday language, undefined means no clear answer. If I asked you what color a sound is, you'd rightly shrug. The question is undefined because the comparison mixes categories that don't match. In math, undefined is a firmer version of that. It means there's no sensible number to assign. The classic example is division by zero. If you try to compute 1 divided by 0, there's no number that makes sense as an answer, because multiplication is the inverse operation and no number times 0 gives 1. So 1/0 is undefined. There are also subtleties like 0/0, which is called indeterminate. It could be many things depending on the context. But the bottom line is that undefined flags a place where the rules we're using break down, and we need to rethink the question or the framework. That idea matters when we talk about removing a black hole from a galaxy. In a real galaxy, you can't simply delete 4 million suns worth of mass from the center without changing things everywhere. Doing so would be an artificial operation that might leave your model with undefined or nonsensical behavior, unless you carefully replace that mass in some consistent way. In other words, if you sweep SGRA out of the center but don't decide how the gravitational field is adjusted, orbit calculations become undefined. Stars that had stable paths suddenly have no place to orbit, and the equations you were solving no longer make physical sense. So any thought experiment about no black hole has to be posed carefully. Do you spread the mass out? Do you redistribute it into stars? Or do you simply take it away and let gravity reconfigure everything? Each choice leads to a different, well-defined scenario and different predictions. Okay, with that bit of housekeeping out of the way, let's look at specific variations. What if the Milky Way's black hole were slightly different? Heavier, lighter, or more active? What do observations of other galaxies and numerical simulations tell us? One way to get insight is by looking outward. The universe includes galaxies with a wide range of central engines. Some galaxies host giant, actively feeding black holes called quasars. These can outshine the combined light of billions of stars while they gorge on gas. Others, like our Milky Way today, are quiet. There are also galaxies where we can't detect any central supermassive black hole at all, or where the nucleus is dominated by a dense cluster of stars instead. That variety is useful because it's like sampling different evolutionary recipes, which ingredients produce which outcomes. Take Milky 7, the giant elliptical galaxy whose black hole was imaged by the Event Horizon Telescope. Its central black hole is billions of times more massive than SGRA, and it was actively launching a powerful jet for a long time. Milky 7 is also a large, red, old galaxy that stopped forming many new stars long ago. Astronomers see a trend. The most massive galaxies tend to have big black holes and low star formation rates. That's not a simple cause and effect law written in stone, but it's a strong statistical correlation, and it hints that energetic black holes can quench star formation in big galaxies by heating and expelling gas. On the other end, many small, irregular galaxies either have weak central black holes or none that we can easily identify. Some of these small galaxies are still actively forming stars because they don't contain enough mass for a central engine to shut everything down. Simulations help tie those observations into a coherent picture. Modern galaxy formation simulations, names you might hear in astronomy circles include Illustris, Eagle, and Fire, try to include the messy physics of gas cooling, star formation, supernovae, and black hole feedback. What the simulations consistently show is that if you don't include black hole feedback, the biggest galaxies end up with too many stars compared to what we actually observe. They become overgrown and too blue, meaning they keep producing young stars for too long. Adding a central black hole that can inject energy at the right times brings the simulated galaxies into much better agreement with reality. Star formation is tamped down in a way that matches the population of observed massive, quenched galaxies. That's a strong clue that black holes do matter on cosmic scales. They help regulate how galaxies grow. But there's nuance. The timing and mode of feedback are crucial. A black hole that grows slowly and peacefully doesn't change much. A black hole that goes through a few brief, intense feeding episodes early in the galaxy's life can punch a hole through the cocoon of cold gas, launching outflows that halt runaway star formation. If the outflows are too strong or too early, the galaxy can be starved and finish forming most of its stars very early, leaving little left later on. If they're too weak, the galaxy remains a star factory. The diversity of outcomes we see in simulations and in the sky mirrors the range of black hole behaviors across different galaxies. In short, it's not just is there a black hole, but how does it behave over time? Now let's bring that back to the Milky Way. Data suggests Sagittarius A didn't always behave as it does now. The Fermi bubbles are a clear sign that several million years ago something energetic happened in the core, an episode of activity that pushed vast amounts of gas and energized particles into two enormous lobes above and below the galactic plane. That event could have been a moderate feeding episode of the black hole, or a concentrated burst of star formation and supernovae in the central region, or some combination. Either way, Sagittarius A has probably flickered through states of higher and lower activity over cosmic time, and each flicker nudged the galaxy's gas budget and star-forming patterns. What about galaxies that truly lack an obvious central black hole? They exist, though they're hard to study because small black holes are faint and nuclear star clusters can mask their presence. M33, a nearby spiral, is a commonly cited example where a central supermassive black hole is either tiny or absent. Studies of such galaxies show that they tend to be less massive, often gas-rich, and actively forming stars. Their central dynamics are different. Rather than a compact, high-speed playpen for stars, you often find more diffuse nuclear star clusters. The existence of such systems tells us two things. One, a galaxy can be perfectly normal in many respects without a big central black hole. Two, the long-term evolution, how quickly it forms stars, how metals build up, whether it quenches early or late, can follow a different path without a powerful central engine. There's also a middle ground worth highlighting. Some galaxies have a nuclear star cluster plus a modest black hole. Those systems illustrate a competition between two ways to concentrate mass in a galactic center. Either gas funnels in and forms many stars there, building a dense stellar cluster, or gas flows feed a black hole that grows and eventually dominates the dynamics. In many cases, both processes occur. Observationally, larger galaxies more often host massive black holes, while lower mass ones show nuclear clusters, implying that the efficiency of black hole formation and growth scales with the galaxy's mass and its ability to feed the central engine. Let's talk about how small changes in central mass affect dynamics. In the inner few parsecs of a galaxy, gravity from the black hole sets orbital speeds and stabilizes or destabilizes gas orbits. If the central mass is reduced, gas and stars that were on tight, rapid orbits slow down and respond to the overall gravitational field of the bulge and the disk. That can change how gas flows inward along a bar structure, for example. Bars are efficient at funneling gas toward the center, and in the presence of a compact massive object, the gas can pile up into rings at specific radii. Without that compact mass, the flow might proceed differently, possibly changing the rate and location of central star formation. So even moderate differences in central mass can shift where stars form and how energy is distributed. Beyond dynamics, there's chemistry. Star formation drives the production of heavy elements through supernovae, and the timing of star formation affects when those elements become available to build rocky planets. If a galaxy burns through its gas early because there's no black hole to regulate things, it may produce a lot of metals early, potentially enabling the formation of rocky planets very early on in cosmic time. But it might also exhaust its gas supply so fast that in later epochs, there are fewer new stars and fewer opportunities for planetary systems like ours to form. If there is a regulating black hole, the enrichment process can be more gradual, spreading useful elements over a longer period, and possibly providing a longer habitable window for planetary systems to arise. Let's bring an example down to human scale. Imagine a city's food supply. If farmers produce everything at once and dump it on the market, the town has a glut for a short time and then a famine later. If instead there is a central warehouse and distribution system that paces deliveries over time, the same total amount of food can sustain the town over decades. Black holes, when they provide feedback, are a bit like that warehouse and distribution system. They don't make elements, but they regulate when and where raw materials turn into stars and spread their enriched products back into the galaxy. Another concrete consequence concerns high-speed stars and tidal drama. Sagittarius A acts as a gravitational pinball machine in the inner region. When a binary star ventures too close, one partner can be captured, while the other gets flung out as a hypervelocity star. We've actually observed stars moving so fast they're likely to be unbound from the Milky Way, and one plausible explanation is such encounters with the central black hole. Remove the black hole and you remove a neat mechanism for producing these intergalactic runaways. Instead, hypervelocity stars might still be produced through other violent processes, like interactions during galaxy mergers or dynamical interactions in dense star clusters. But the statistics will differ. There's also the question of tidal disruption events, stars that stray close enough to be ripped apart by the black hole's tidal forces. These rare but spectacular flares allow astronomers to infer the presence of a central massive object even in otherwise quiet galaxies. Without a supermassive black hole, we'd see far fewer of these flares. That changes the high-energy history of the galaxy's core, with knock-on effects on ionization and heating of certain gas phases. And then there's gravitational waves. The mergers of massive black holes during galaxy collisions are among the loudest gravitational wave events in the low-frequency band, the sort that a future space-based detector called LISA hopes to hear. If a galaxy lacked a central black hole, or if its black hole population were systematically different, the gravitational wave sky would look different. For gravitational wave astronomers, central black holes are both a target and a tool. They tell us about galaxy merger histories and about strong gravity. So far, most of this is about variation and consequences. There's another key subject that connects to both black hole physics and the notion of undefined. The problem of seeds. How do supermassive black holes form in the first place? Observations show quasars, massive black holes accreting at enormous rates, already when the universe was less than 1 billion years old. That's surprisingly quick growth, and it sets up questions that are still being actively researched. There are a few leading ideas for initial seeds. One is that the first generation of stars, very massive, short-lived population III stars, died and left behind black hole remnants of tens to hundreds of solar masses. Over cosmic time, those seeds accreted gas and merged, stepping up to larger masses. Another idea is direct collapse. Under some special conditions, a massive gas cloud could avoid fragmenting into stars, and instead collapse almost directly into a black hole of maybe 10·4 to 10·5 solar masses. Which of these pathways dominates likely depends on environment and timing, and the universe may have used multiple channels. Why does that matter for our no black hole thought experiment? Because if seed formation is efficient, black holes may be almost inevitable in galaxy centers. If seeds are rare or require special conditions, some galaxies could easily end up without a supermassive black hole. Observationally, the situation is mixed. Many galaxies do seem to host SMBHs, but a meaningful fraction, especially at lower masses, either lack a detectable one or host only a modest black hole. That tells us nature doesn't have a single recipe but a variety of channels, which in turn affects how common no black hole galaxies are. Let's zoom into Earth-relevant details. Could removing Sagittarius A meaningfully change the environment of the solar system? Probably not in a direct, catastrophic way. The Sun orbits the galactic center at a safe distance of about 26,000 light-years, so most local dynamics are set by the mass distribution of the disk and dark matter halo. Removing a small central mass would not fling the Sun out of its orbit or change Earth's climate directly. But indirectly, over billions of years, the same processes that shape the galaxy's star formation history and chemical evolution could shift the timing and frequency of supernovae, gamma-ray bursts, and the birthplaces of stars. Those changes could alter the background radiation environment, the rate at which heavy elements become available, and the probability that a star like the Sun forms with planets in the right place and with the right composition. These are statistical, long-term effects rather than immediate threats. That leads to another important idea: probability versus inevitability. A central black hole doesn't make life inevitable, and its absence doesn't make life impossible. What black holes do is influence the likelihood of certain paths. By modulating the flow of gas and the tempo of star formation, they affect the odds that a given galaxy will produce planetary systems with the right mix of elements at the right times. Think sportily. Removing a star player doesn't guarantee your team loses every game, but it changes your odds across a season. Let's pull in some numbers to make the ideas concrete without getting bogged down in heavy math. Sagittarius A has roughly 4 million solar masses. The Milky Way as a whole has something like a few hundred billion stars and a total mass, including dark matter, of the order of 10-12 solar masses. That tells you how small the black hole is by mass compared with the galaxy overall. Yet the energy released when matter falls into a black hole can be enormous. A few percent of the mass energy of the infalling matter can be converted into radiation and kinetic outflows, which for astrophysical purposes is an extremely efficient energy conversion. That's why a relatively small amount of mass falling onto a black hole during an active episode can have a big impact on surrounding gas. Consider the Fermi bubbles again. They extend for roughly 25,000 light-years end to end, and their energy content is equivalent to the combined output of millions of supernovae over a relatively short time. That kind of event doesn't require a black hole with a huge fraction of the galaxy's mass. It can be produced by a modest feeding episode. That's the practical point. Power matters more than mass when it comes to influencing the galactic environment. A quiet, massive black hole is less impactful than a smaller one that suddenly starts eating a lot. How do astronomers test these ideas further? Observations across wavelengths, radio, infrared, X-ray, gamma-ray, reveal different parts of the story. Radio maps trace jets and magnetic fields. X-rays reveal hot gas. Infrared sees the dusty star-forming regions that optical telescopes can't see through. Surveys of many galaxies give the statistics that let researchers see correlations between black hole mass, galaxy mass, star formation rate, and other properties. Meanwhile, increasingly sophisticated simulations try to replicate those correlations by tweaking how black holes accrete and deposit energy into their surroundings. When simulations that include plausible black hole physics reproduce observed distributions of galaxies, that strengthens the case that black holes are key players. There are still puzzles. For example, the exact mechanism by which accreting black holes launch powerful, collimated jets is not fully understood. Magnetic fields almost certainly play a role, and the spin of the black hole might be a factor, but the detailed physics of jet production and the coupling of that jet energy to the surrounding gas are active areas of research. That's one reason observational studies of nearby black holes like SGR-A are so valuable. They provide a high-resolution laboratory for testing models. One more practical complication is that galaxies live in environments that influence them too. The Milky Way didn't evolve in isolation. It's part of a small grouping of galaxies that includes Andromeda and dozens of dwarf companions. Interactions and mergers drive gas inward, can trigger black hole feeding episodes, and can alter the distribution of angular momentum in the disk. So a galaxy without a central black hole might evolve differently depending on whether it lives in a crowded neighborhood full of mergers or out in the field with fewer interactions. In fact, many of the most massive black holes probably grew in part through successive mergers of smaller black holes during galaxy collisions. Remove that channel and the population landscape changes. Finally, let's revisit the idea of undefined from a computational perspective. When astrophysicists build a simulation and decide to remove the central black hole, they need to do it in a way that keeps the physics defined. That might mean redistributing the mass into a smooth bulge, or injecting the equivalent gravitational potential into the surrounding stars. If they simply set the central mass to zero, the orbits that were integrated under one potential suddenly become invalid under another, and the code has to re-equilibrate the system. In practice, researchers run controlled experiments where they compare with black hole and without black hole scenarios, but they do so by replacing the black hole with well-defined, physically consistent alternatives. That way their models remain defined, and the predictions they make about star formation, gas flows, and structural evolution are meaningful. All of this gives us a sharper picture. The presence or absence of a central black hole, as well as its mass and feeding history, are important pieces of the puzzle of how a galaxy grows and changes. Black holes act as regulators, potential agitators, and seeds for a variety of dramatic phenomena, from jets and bubbles to hypervelocity stars and gravitational wave events. Removing a black hole changes the dynamics and thermodynamics of the central region, and those changes ripple outward over billions of years, altering the galaxy's star formation history, chemical enrichment patterns, and the probability distribution for habitable environments. But the absence of a black hole does not automatically doom a galaxy to sterility, nor does the presence of a black hole guarantee life-friendly conditions. Instead, central black holes are one of many interacting actors in a long, complicated cosmic drama. There are still many details to explore. Next, it's worth diving deeper into specific case studies and simulation results to see exactly how sensitive planetary system formation and long-term habitability are to the presence of a central black hole. We can compare galaxies across the mass scale, examine how black hole activity correlates with metal production and retention, and look at observational signatures that tell us which galaxies had energetic black hole episodes in their pasts. We can also dig into the physics of seeds and early growth. How did the first black holes get started, and could a universe without those early seeds look substantially different? Each of these directions helps sharpen our understanding of what role black holes play in making some galactic neighborhoods more conducive to complex chemistry, planets, and maybe life. If we want to move from general ideas to something more concrete, the most natural place to look is at real galaxies and at the computer universes astronomers build to test ideas. Observations give us examples, galaxies that are loud with their central engines and galaxies that whisper, while numerical simulations let us tweak parameters and watch whole cosmic histories unfold. Together they form the best evidence we have for what a black hole does to a galaxy and what happens if it's missing or behaves differently. Start with the observed variety. Some galaxies host tremendously active central black holes, quasars, that light up as they gobble gas and can outshine the rest of their galaxy. Others show modest activity, like Seyfert galaxies, and many more are essentially quiescent, with only faint, hard-to-detect signs of a central mass. Then there are systems where the signature of a supermassive black hole is weak or absent, and instead we find a dense crowd of stars in the center, a nuclear star cluster. These differences are not random. They tend to correlate with a galaxy's mass, its environment, and its past interactions. Massive elliptical galaxies, which live in dense environments and have histories filled with mergers, are far more likely to host giant, active black holes. Small, late-type spiral galaxies often have much smaller black holes or none that are obvious. Why does that pattern matter? Because it tells a story about feeding and growth. When a galaxy experiences a major merger, two comparably massive galaxies colliding and combining, tidal forces funnel large amounts of gas toward the center. That feeding frenzy can starve the outer disk and light up the central black hole. In some systems, this results in a quasar phase, a bright, energetic episode that lasts perhaps tens to hundreds of millions of years, long enough to change the structure and composition of the host galaxy. If mergers and gas-rich inflows are rare, the central black hole may remain small and quiet. So whether a galaxy's black hole plays a major role depends not just on the black hole's mass, but on how often it gets fed. Simulations let us explore those histories systematically. Modern cosmological simulations, the ones meant to reproduce large swaths of the observable universe, include recipes for how gas cools, forms stars, and how energy from stars and black holes couples back to the gas. Two consistent results stand out. First, without black hole feedback, simulations tend to produce galaxies that are too massive and too blue compared to what we see. They form far more stars than real galaxies of similar mass. Second, when black holes are included with plausible feedback prescriptions, the simulated population becomes a much better match to observations. That's a strong, if statistical, argument that black holes play a regulatory role in shaping galaxy populations. There's a caveat worth emphasizing. Black hole feedback is a catch-all term that can mean very different things in different circumstances. At high accretion rates, a black hole's energy output is dominated by radiation. That radiative mode can heat and ionize gas, and in some cases drive powerful winds. Think of a quasar blasting the surrounding gas with intense light. Photons transfer momentum to particles and can push gas away. At lower accretion rates, mechanical feedback, jets and collimated outflows becomes important. These jets can punch through the galactic medium, inflate bubbles of hot plasma, and heat gas at much larger distances. Astronomers often call these the quasar mode and the radio mode, and both can be effective in different contexts. For a Milky Way-like galaxy, episodic moderate activity, enough to blow bubbles and stir the inner halo, may be more important than an all-out quasar phase. The Milky Way itself provides a useful case study precisely because Sagittarius A is relatively quiet now, but has clearly been active in the recent past. The Fermi bubbles are the smoking gun. Huge lobes of energetic particles and gamma raise that point to an energetic event at the center a few million years ago. That event didn't sterilize the galaxy, but it did push gas out of the central regions, likely altering the immediate supply of cold gas for star formation. It's an example of how even a moderate feeding episode can reshape the gas reservoir on multi-kiloparsec scales. Now let's look at a few illustrative alternative scenarios, which help make the differences clear. Scenario A. Remove the black hole's mass entirely and don't replace it. This is the most artificial thought experiment because it creates a discontinuity. A compact 4 million solar mass object disappears, and the gravitational potential changes instantly. In a physical sense, you'd have to move that mass somewhere. You can't just banish it without consequences. If you forced such an instantaneous removal in a simulation, the central stars and gas would find themselves in new orbits that could be chaotic. Some might move outward, some might collide. The result would be an impulsive readjustment of the central region. But because you've violated mass conservation in an unrealistic way, the outcome is not a useful model of real galaxy evolution. Scenario B. Spread the black hole's mass smoothly into the central bulge. This is a cleaner choice for a simulation. You replace the concentrated mass by an equivalent amount of mass distributed across the central parsecs or tens of parsecs. In this case, the gravitational potential is shallower in the central point and deeper at larger radii, but mass-conserving overall. The innermost star orbits lengthen, gas dynamics change, and processes that depend strongly on a point like gravity, like tidal disruptions or hypervelocity star production, virtually disappear. But the large-scale potential of the galaxy barely changes, so the Sun's orbit and the structure of the disk are almost untouched. The bigger effect will be on the central gas flows. Without a steep potential well, gas may stall or pile up differently, altering where and when it forms stars. Scenario C. Keep the black hole's mass but forbid it from accreting a dead black hole. This is also a useful case, because it isolates the dynamical role of mass from the energetic role of accretion. You still have a compact gravitational anchor, so the orbits of stars very close in remain the same, but the feedback that would otherwise heat and expel gas is absent. The central gas can collapse more easily, potentially forming more stars in the nuclear region. This leads to a galaxy with a denser central stellar population and potentially different metal distributions. Observationally, a nuclear star cluster might form rather than a dominant active nucleus. These scenarios show why thought experiments must be precise. No black hole can mean very different things. They also reveal which effects are local change within the inner parsec, and which ripple outward central star formation, gas flows, chemical enrichment. Replacing a compact mass with diffuse mass affects processes that depend on strong, localized gravity. Shutting off accretion alters energy feedback, and therefore the thermal and dynamic state of gas at kiloparsec scales. Let's unpack some of the consequences in more detail, especially those relevant to planet formation and habitability over cosmic time. Two broad threads matter most for the long-term potential for life: chemical enrichment and the radiation environment. Chemical enrichment is the process by which successive generations of stars make heavier elements, carbon, oxygen, silicon, iron, and return them to the interstellar medium via winds and supernovae. The timing and distribution of enrichment determine where and when rocky planets can form, and whether those planets have the raw materials for chemistry and biology. If a galaxy undergoes a rapid, early starburst and produces lots of metals quickly, rocky planets can form early. But if that early burst uses up the gas reservoir, later generations of star formation may be suppressed, limiting the production of new planetary systems in the long term. Black hole feedback can slow down and prolong star formation, spreading enrichment over longer timescales and potentially widening the window during which habitable planets may form. This is the warehouse and distribution analogy again. The black hole helps pace when material is converted into stars. The radiation environment is complementary. High-energy outbursts from an active nucleus produce X-rays, ultraviolet light, and cosmic rays that can change the chemistry of gas clouds and potentially affect planetary atmospheres if the flux reaches star systems. For the Milky Way, even significant central activity is generally too far away to catastrophically alter Earth's biosphere. Galaxies that host extremely luminous quasars, on the other hand, can create regions where high-energy radiation is intense within a few kiloparsecs. The net effect on habitability is complicated. While intense radiation can strip atmospheres from planets close to the galactic center or change the chemistry of protoplanetary disks, moderate amounts of energetic particles can also catalyze certain chemical pathways that might be relevant to prebiotic chemistry. Overall, black hole activity tends to make the inner galaxy a harsher environment while leaving the outer disk relatively safe. Another important factor is the circumgalactic medium, the halo of gas that surrounds a galaxy out to hundreds of kiloparsecs. Black hole outflows can heat and enrich this halo, affecting how gas cools and falls back to the disk. A hotter, more turbulent halo delays the replenishment of cold gas, which can slow down future star formation. Conversely, without such heating, gas may accrete more steadily and fuel longer-lived star formation in some galaxies. This interplay affects the star formation history, and therefore the production rate of supernovae and massive stars that seed the interstellar medium with heavy elements, and it feeds back into planet formation prospects. In short, the actions of a central black hole have consequences that reach well beyond the visible bulge. We can make some of these ideas more tangible with numbers and timescales. The Fermi bubbles are evidence of a central event on the order of a few million years old. A quasar phase that dramatically changes a galaxy's star formation might last 10·7·10·8 years, short on cosmological timescales, but long enough to have lasting consequences. Galactic chemical evolution unfolds over billions of years. The metallicity of stars at any radius traces the integrated history of star formation there. If a black hole's feedback shifted the galaxy's star formation rate by a factor of 2 at Z2, around 10 billion years ago, that would significantly change the distribution of metallicities today. Those differences are measurable. Astronomers compare metallicity gradients in galaxies of different types to infer histories of inflow, outflow, and feedback. Another way black holes leave fingerprints is through dynamical signatures. The M-sigma relation, a tight correlation between the mass of a galaxy's central black hole, M, and the velocity dispersion, sigma, of its bulge stars, is a statistical clue that black holes and bulges grow together. If many galaxies lacked central black holes, or if their masses were unrelated to bulge properties, this relation would be much looser. Observations show scatter, but the existence of the correlation suggests a coupling mechanism, presumably feedback that ties black hole growth to bulge growth. The details of that coupling are still debated, but the correlation itself rules out some extreme no-black hole universes. Let's not forget gravitational waves. The mergers of black holes during galaxy collisions produce gravitational radiation. If a galaxy population had a very different black hole demographic, fewer or smaller central black holes, the low-frequency gravitational wave background that future detectors like LISA hope to detect would be altered. That background encodes the history of black hole mergers across cosmic time. A universe with systematically fewer SMBHs, or with a different seed formation mechanism, would sing a different gravitational wave tune. For astronomers, that's not just academic. It's a concrete observational test that will, in the coming decades, give new constraints on how common different black hole formation pathways are. There are also local dynamical stories worth following. The inner parsec of a galaxy is a crowded place. In the Milky Way, there's a population of so-called S-stars orbiting Sagittarius A on elliptical paths that provide direct evidence of a compact mass. If you remove that compact mass and spread it out, those tight orbits can't be maintained. The dynamics of compact stellar remnants, neutron stars and stellar mass black holes, change, and the rates of close encounters, collisions, and mergers shift. In one scenario, the absence of a central SMBH increases stellar collisions in the very core because stars are less tightly bound and can wander into intersecting paths. In another, the presence of a compact mass concentrates interactions and increases the production of gravitational wave sources through extreme mass ratio inspirals. Both situations offer different observational signatures. Observationally, there are galaxies that illustrate both extremes. M33, the Triangulum galaxy, is a nearby spiral where a substantial central black hole is not clearly detected. Its nucleus is dominated by stars rather than a bright central engine. MADI 7 is the opposite extreme, with a supermassive, jet-launching black hole that has reshaped its environment. A third class includes galaxies with dense nuclear star clusters that may or may not harbor a modest SMBH. These examples tell us that nature produces a range of central configurations, and that range must be accounted for in theories of galaxy formation. Taking another step into specifics, think about bars and gas inflows in disk galaxies. Bars are non-axisymmetric features in disks that torque gas and send it inward. In the presence of a compact central mass, inflowing gas can pile up at certain resonances and form circumnuclear rings of star formation. Without that compact mass, gas can continue inward or settle differently, potentially feeding a central star cluster rather than a point-like black hole. So whether a galaxy forms a nuclear cluster or a supermassive black hole, as its central concentration may depend on the interplay between structural features like bars and the central potential. Over cosmic time, repeated episodes of inflow and star formation can build a dense stellar core that competes with or even prevents efficient black hole growth in some mass ranges. One of the still open questions is how supermassive black holes get their start in the first place. We see quasars at very high redshift, when the universe was less than 1 billion years old, which implies that seeds had to form and grow quickly. There are two major seed scenarios in play. In one, early massive stars, so-called population III stars, die and leave behind black holes of tens to a few hundred solar masses. These seeds then grow by accretion and mergers. In the other, under rare special conditions, a dense gas cloud collapses almost directly into a black hole of 10^10^5 solar masses, a direct collapse black hole. Which channel dominates matters. If seeds are typically small, then the growth histories needed to reach billion solar mass quasars by Z6 are extreme and require sustained high accretion rates. If seeds can be large from the start, then reaching those masses is easier. The distribution of seeds influences how common supermassive black holes are in lower mass galaxies today. If seeds are rare, many dwarf galaxies would lack them. If seeds are common, most galaxies might host at least a modest central black hole. This touches a subtle observational point. Searching for small black holes in small galaxies is hard. A low-mass black hole accreting at a low rate is faint, and a dense nuclear star cluster can hide dynamical signatures. That means our census of SMBH is incomplete, especially at the low-mass end. Some dwarf galaxies have shown convincing evidence for central black holes, even ones of only a few thousand solar masses, while others show no sign. As observational techniques improve, particularly with sensitive X-ray and radio surveys, and with future extremely large telescopes that can resolve central stellar motions, we'll get a more complete picture. Another direction to explore is how the presence or absence of a central black hole changes the pattern of explosive events that shape life's environment. Supernovae and gamma-ray bursts. These events are mostly tied to massive star populations, so they follow the star formation history. A galaxy that forms stars in intense bursts will produce many massive stars, and therefore many supernovae and a higher chance of a nearby gamma-ray burst at some epoch. If black hole feedback smooths and paces star formation, it reduces the risk of concentrated periods with many nearby deadly explosions. For life that needs long windows of relative stability, that pacing could be important. But again, this is probabilistic. Local conditions, birth cluster density, proximity to star-forming regions, and the sun's eventual migration play large roles. We can also imagine future changes. The Milky Way is on a slow-motion collision course with Andromeda. In a few billion years, the two galaxies will merge, and their central black holes will likely find each other and eventually coalesce. That process will probably produce a bright AGN phase as infalling gas feeds the growing black holes, and later, a gravitational wave signal when the black holes merge. If the Milky Way lacked a central black hole, the merger would look quite different. The merged galaxy might end up with a single black hole only if one formed later through direct collapse or accumulation of compact remnants. Otherwise, the resulting dynamics could produce a dense nuclear cluster instead. That changes the future structural path of our local group, and it changes what sort of central engine might influence the galaxy after the merger. From the perspective of planetary systems, most of the action that directly affects a planet's climate and atmosphere is local to the star and its immediate neighborhood. Still, over billions of years, the galactic environment matters. The Sun formed about 4.6 billion years ago, in a galaxy that had already undergone significant chemical enrichment. If the Milky Way's central black hole had suppressed or accelerated certain episodes of star formation earlier in the galaxy's history, the Sun's birth environment might have had a slightly different metallicity, potentially altering the composition of the Earth. These differences would be subtle but measurable in principle. Isotopic ratios, abundances of certain elements, and the distribution of short-lived radionuclides in the early solar system could reflect differences in nearby supernova rates, which in turn are tied to galactic star formation histories. For those interested in the philosophical side, there's an anthropic twist. We observe life in a galaxy that has a supermassive black hole. That observation is necessarily conditioned on the fact that we exist here to observe it. You can't conclude from one example that black holes are necessary for life, but you can note that their presence is compatible with life's emergence in at least one case. Large statistical studies of exoplanet occurrence, stellar metallicities, galactic environments, and life-hosting candidates might one day give better answers about whether life is likelier in galaxies with certain central engine histories. For now, the evidence suggests black holes are an important piece of the galactic ecosystem, but not an absolute gatekeeper for habitability. Returning to observational tests, astronomers are already using multi-wavelength diagnostics to tease out black hole activity histories. X-ray observations probe hot gas and accretion flows, radio maps trace jets and lobes, infrared sees dust-obscured star formation, and optical spectroscopy measures ionized gas that can be excited either by young stars or by a hard AGN radiation field. By combining these signals, it's possible to reconstruct the timing and intensity of central activity. For instance, the chemical composition of gas at different radii can reveal whether metals have been expelled into the halo, and the presence of high-velocity outflows in absorption line studies can signal AGN-driven winds. These diagnostics allow astronomers to identify galaxies that have undergone AGN episodes, even if those episodes ended millions of years ago. Another active area is trying to understand how energy couples to the gas. Jets are efficient at delivering mechanical energy far from the central engine, but they affect only narrow regions unless their energy is redistributed by interactions with the surrounding medium. Radiative winds are more isotropic but can be inefficient if the photons escape through low-density channels. The precise microphysics, how magnetic fields mediate jet launching, how radiation couples to dusty clouds, how shocks heat and accelerate gas, determines the macroscopic effects we measure. That's why detailed observations of nearby systems like the Milky Way are so valuable. They give boundary conditions for models and tell us which microphysical assumptions produce realistic macroscopic behavior. We should also highlight how future facilities will sharpen this picture. A new generation of giant ground-based telescopes will resolve stellar motions in more distant galactic centers, allowing direct dynamical measurement of black hole masses in many more galaxies. Space-based detectors like LISA will probe the population of merging black holes, giving independent constraints on formation histories. Improved X-ray and radio facilities will provide deeper surveys for faint AGN in dwarf galaxies, filling in the low-mass end of the black hole census. All of these data will constrain how often black holes are truly absent versus simply hidden or quiescent. Finally, there's a practical modeling point. When astrophysicists run what-if simulations, they often compare runs that differ only in one ingredient. That controlled approach is the only way to isolate cause and effect. For example, one set of simulations might include realistic black hole accretion and feedback, while a companion set removes that feedback but keeps the mass. Another set might replace the black hole with a smooth bulge of equal mass. By comparing the outcomes, star formation histories, morphology, metallicity gradients, and kinematics, researchers can separate the dynamical effects of mass from the thermodynamic effects of energy injection. Those comparisons make clear that both aspects matter, but they also show which galactic features are robust to removing the black hole and which are sensitive. Taken together, the observational record and simulation results sketch a consistent picture. Supermassive black holes are not omnipotent dictators of galactic fate, but they are important regulators and occasional agitators. They exert strong local influence in galactic centers, and through energetic feedback they can heat and displace gas on much larger scales, altering star formation histories and chemical enrichment. The degree to which they matter depends on their mass, their feeding history, and the galaxy's context, how often it merges, how much gas it holds, and what structural features, like bars, are present. A galaxy without a central black hole could look surprisingly normal in many ways, but it would likely show measurable differences. A different central structure, altered rates of certain transient events, and a distinct evolutionary trajectory for star formation and metal distribution. Those differences ripple into questions about planets and life, but mostly as statistical nudges rather than deterministic prescriptions. Black holes shape the probabilities. They influence when heavy elements become available and how violently a galaxy's environment may change over time. If you want to predict whether a given galaxy is a fertile place for life, you need to fold in the black hole's history along with many other factors: the galaxy's mass, merger history, local stellar density, and the timing of star formation. In the end, black holes are an essential chapter in the story of galaxies, a chapter that matters for how those galaxies evolve, and by extension, for the long-term chances that planets like ours appear and persist. Let's pick up one especially useful thread and follow it where it leads: the idea of a galactic habitable zone. Astronomers sometimes talk about habitability not just around individual stars, but across whole galaxies. Which regions are more likely to make and keep planets that could host life? It's a handy way to translate the broad, slow changes driven by things like black holes into more tangible ideas about planets and biology. Think of the Milky Way as a map with gradations of friendliness. Close to the center, you tend to find higher metallicity, that is, gas enriched in heavy elements like iron, silicon, oxygen, the building blocks of rocky planets. That's a pro, but the center is also where things are crowded. More stars, more supernovae, denser radiation fields, occasional energetic flares from the central engine. That's a con. Far out in the disk, you get safer neighborhoods with fewer catastrophic events and slower, steadier star formation, but the gas there can be more metal-poor, which can make it harder to build Earth-like planets. Because black holes influence both star formation tempo and how metals are distributed, they indirectly shift the shape of this habitable map. How exactly? One clear mechanism is by pacing star formation. If a central black hole puffs hot gas into the halo, or drives winds that temporarily remove cold gas from the inner galaxy, it can delay a burst of star formation in the bulge. Delayed star formation spreads the production of metals over longer times, which, in principle, increases the chance that planets form over a wide swath of time, rather than in one brief, intense epoch. That stretching of the planet formation timetable matters for habitability in a statistical sense. It increases the duration during which potentially habitable planetary systems can appear. If the black hole were absent and the inner galaxy converted gas into stars in a short, intense burst early on, you could end up with many metal-rich stars early, but a depleted reservoir later. Fewer new stars and planetary systems forming when conditions might be calmer. There's also a radial effect. When energetic outflows push gas out of the disk, they don't always eject it to intergalactic space. Often it gets lofted into the halo, mixes, cools, and rains back down at larger radii. That process can flatten metallicity gradients, making the outer disk more metal-enriched than it would be otherwise. Or it can push metals entirely out of the galaxy if the outflows are strong enough. Both outcomes depend on how energetic the central engine is. So a black hole's activity can help populate the mid-disk with heavier elements, potentially enlarging regions where rocky planets can form. Conversely, an overly violent episode could strip metals and slow planet formation across the whole galaxy for a long time. Now let's put numbers to some of this thinking so the scale is clearer. The Sun sits around 8 kiloparsecs, about 26,000 light-years, from the galactic center, safely in the disk rather than the bulge. That's partly why Earth has enjoyed a relatively stable environment. It's far enough from the crowded, violent inner regions. If you move the Sun inward, toward the bulge, the odds of encountering a nearby supernova or strong radiation episode increase. Move it outward, and you run the risk of lower metallicity, depending on the Milky Way's metallicity gradient. The black hole's imprint on where and when metals get distributed therefore nudges how large the comfortable annulus, the galactic habitable zone, is and where it sits. So far we've been talking qualitatively. To test these ideas, astronomers use simulations. Modern cosmological simulations are powerful but also complicated beasts. Think of them as virtual universes where we try to model gravity, gas physics, star formation, supernova explosions, and the messy, small-scale processes we can't resolve directly. Because we can't simulate every atom, simulators include subgrid recipes, simplified models that describe the average effects of small-scale physics on larger scales. The crucial point is that different assumptions about how black holes accrete and how their energy couples to gas produce different galactic outcomes. Some of the best-known simulation projects, names you'll hear tossed around, are Illustris, Eagle, Fire, and TNG, have converged on a general lesson. You don't get realistic massive galaxies without including some form of black hole feedback. If you simulate a galaxy like the Milky Way without an energetic central engine, the result tends to be a galaxy that forms too many stars and too early. The disks become too massive, and the central bulges too big relative to what we observe. Add a plausible black hole with episodes of feedback, and the simulated population better matches what telescopes actually see. A mix of star-forming and quenched galaxies, realistic stellar masses, and believable metallicity gradients. That's a strong point, but it comes with a long list of caveats. Plausible feedback models vary. Some deposit energy thermally into surrounding gas, some push gas mechanically as jets, some do a combination. The effectiveness of a feedback episode depends on the local gas density, the way the energy is deposited, how long it persists, and whether the galaxy is in a merger or a quieter phase. Because the subgrid recipes differ across simulation codes, one needs caution in drawing absolute conclusions. Still, the qualitative lesson stands. Energetic feedback is an important lever for shaping galaxies, and black holes are an efficient lever. If you prefer observational examples, there are real galaxies that illustrate both ends of the spectrum. Mate 7, a giant elliptical in the Virgo cluster, shows a very massive black hole and powerful jets. It is a red, quiescent galaxy that formed most of its stars long ago, and now produces very few new ones. M33, the Triangulum galaxy, is often cited as a galaxy where a massive central black hole either doesn't exist or is far smaller than in similar-sized galaxies. Its nucleus is dominated by stars rather than a bright AGN. M33 is actively forming stars and is metal-poor compared with the Milky Way. These cases don't prove causation. Galaxies differ in many ways, and environment and merger history matter, but they provide a laboratory for thinking about how central engines can tilt the evolutionary outcome. Another observational angle comes from relics of past central activity, and the Milky Way offers striking examples. We mentioned the Fermi bubbles earlier, two massive lobes of gamma-ray emission extending above and below the galactic plane. They point to an energetic event at the center a few million years ago. Astronomers have also detected X-ray echoes, shells of hot gas, and ionized gas structures that trace past AGN-like episodes. These relics provide clues about the scale and timing of past feedback and help constrain models of how often our black hole has flared up and by how much. If the Milky Way had no central black hole, we would lack such signatures, or they would require a different explanation, such as a past starburst of particularly intense supernova activity. Let's broaden the picture a bit. Black holes are not the only regulators of galactic evolution. Massive stars and their supernovae are also efficient at stirring and heating gas, especially in smaller galaxies, where a few clustered supernovae can drive large-scale winds. In recent years, the role of stellar feedback has been emphasized more and more, particularly for low and intermediate mass galaxies. In those systems, supernova-driven outflows can flatten central dark matter cusps, regulate star formation, and expel metals. The upshot is that in low-mass galaxies, the presence or absence of a supermassive black hole might matter less for global evolution because stellar processes dominate. In massive galaxies, however, below a certain mass threshold, stellar feedback alone can't prevent runaway cooling. That's where black hole feedback becomes the key player. This division helps explain why the census of black holes is mass-dependent. Big galaxies almost always show evidence of central black holes. Smaller ones often do not. It's not that black holes are magically absent below some mass, more a reflection of nurture versus nature. The relative importance of different feedback mechanisms shifts with galaxy mass. Nuclear star clusters often appear in lower mass systems, dense agglomerations of stars in the center that can dominate the dynamics there instead of a point-like black hole. In some galaxies, you can have both, a nuclear star cluster plus a modest black hole. The competition between forming a dense cluster of stars or growing a black hole depends on the inflow rate of gas and the conditions in the center when those inflows occur. That competition has practical consequences for observations and for the no black hole thought experiment. If you remove a central SMBH and instead have the same mass spread into a dense cluster of stars, you change the inner dynamics dramatically. For instance, tidal disruption events, the bright flares that occur when a star wanders too close to a black hole and is torn apart, would largely vanish. Hypervelocity stars produced by the gravitational slingshot mechanism would be rarer. The gravitational wave signals that come from small compact objects spiraling into a huge black hole, the so-called extreme mass ratio inspirals, would not be present. Each of these specific phenomena is a fingerprint of a compact central mass. We can even push some of these implications into the realm of speculative, but interesting consequences for panspermia, the idea that life can travel between stars. Hypervelocity stars launched by a central black hole could act as tiny life carriers on cosmological highways. If a planet harbored robust microbial life, being ejected at high speed could transport that biosphere out of the galaxy, or at least into very different environments. Without an SMBH, those specific vehicles for interstellar transfer become rarer, so one hypothetical pathway for long-distance life transport would be curtailed. That's not a central factor in life's likelihood, but it is a curious illustration of how a central engine affects even exotic channels. There's also an enlightening connection to gravitational wave astronomy. When massive galaxies merge, their central black holes eventually find each other and coalesce. These mergers are prime sources for low-frequency gravitational waves that future detectors like LISA, a space-based gravitational wave observatory, aim to catch. The amplitude and frequency of the stochastic gravitational wave background measured by pulsar timing arrays also encodes the history of SMBH mergers. If SMBHs were systematically absent in some class of galaxies, the predicted gravitational wave background would be lower. As gravitational wave astronomy matures, it will provide an independent check on SMBH demography, complementing electromagnetic observations. Another piece worth expanding is the origin story. How black holes got their start. We touched on seeds earlier, but the seed question matters because it sets the initial conditions for whether a galaxy ends up with a centrally dominant object. If the universe commonly made large seeds via direct collapse, then many galaxies would naturally grow SMBHs. If seeds were rare or small, some galaxies would remain without a substantial central BH. Observationally, detecting black holes in dwarf galaxies provides clues. Finding many low-mass black holes suggests seeds were common. Failing to find them suggests otherwise. The current picture is mixed. Some dwarf galaxies show clear AGN signatures or dynamical evidence for low-mass SMBHs, while others show none. Improving the census, with deeper X-ray, radio, and dynamical surveys, is an active area because it directly informs the early universe physics of black hole formation. Returning to the Milky Way for a moment, there's an interesting timescale story. The Sun formed about 4.6 billion years ago, and the galaxy at that time already had a complex, evolved chemical structure. Observations of stellar ages and metallicities show that the Milky Way likely experienced different phases of star formation. An early, rapid phase that built much of the bulge and thick disk, and a more prolonged, steady phase that created the thin disk where the Sun sits. Central black hole activity, occurring as episodic bursts, could have played a role in shaping those phases by modulating how quickly the central gas reservoir turned into stars. If SGR-A had been much more active at epochs relevant to the Sun's birth, it might have altered the chemical environment of the protosolar cloud, for instance affecting the abundance of short-lived radionuclides injected by nearby supernovae, and thereby changed some aspects of planetary formation. These effects are subtle and layered on many local processes, but they are another strand tying black holes to planetary systems. When we look forward, there's also the long-term future to think about. In a few billion years, the Milky Way and Andromeda will collide and merge. That event will drastically reshape both galaxies, funneling gas toward the newly forming central region, and almost certainly feeding the central black holes into a brighter, more active state. If the Milky Way lacked an SMBH at that stage, the post-merger nucleus would likely form a dense nuclear star cluster instead, or a new black hole might form from coalescing compact remnants or direct collapse in the gas-rich environment. The choice of central architecture affects the merged galaxy's further evolution, including whether it becomes a quiescent elliptical or a star-forming disk. So the presence or absence of a black hole today informs the far future of our local galactic environment. Throughout this discussion, one recurring theme is that the difference between presence and absence of a black hole is not simply binary. There is a continuous spectrum: tiny seeds, low-mass active galactic nuclei, quiet mid-sized black holes, and the enormous beasts in giant ellipticals. Each point on that spectrum exerts different influences. That spectrum also couples to environment. Galaxies in dense clusters experience more mergers, which tends to grow bigger black holes. Isolated galaxies may evolve more gently and retain smaller central concentrations. So when we imagine a Milky Way without SGR-A, we should imagine where along that spectrum we've moved. Do we have no compact mass at all, or do we have a dense stellar cluster, or a modest black hole that never fed? Another subtle avenue is the effect on dark matter profiles. There's an ongoing debate about whether energetic feedback from stars or black holes can puff up the central dark matter cusp predicted by cold dark matter simulations into a less dense core. Repeated gas outflows that remove and then reaccrete mass can transfer energy to the dark matter, flattening its inner profile. Black hole-driven outflows are capable of powerful, centrally concentrated episodes that could contribute to this process in massive galaxies. If the central black hole were absent, some of that core creation mechanism might be weaker, possibly leaving a steeper dark matter cusp. This is an area of active research because it ties the astrophysics of baryons, normal matter, to the distribution of dark matter, and therefore to predictions about rotation curves and mass distributions in galaxies. Observationally, the hunt for SMBHs in small galaxies is moving forward rapidly thanks to new instruments. Sensitive X-ray telescopes can detect faint accretion signatures. High-resolution radio surveys can pick up jets or compact cores. And the next generation of giant ground-based optical telescopes will resolve stellar motions in nuclear regions to weigh whatever mass is there. The combination of these tools will either fill in the census of low-mass black holes or confirm that some galaxies truly lack them. Each outcome constrains models of seed formation and growth. It's also worth discussing how we might distinguish, observationally, whether a particular galaxy's central engine is a black hole or a dense star cluster when both could explain some features. One approach is dynamics. A compact object exerts a very steep gravitational potential that produces high stellar velocities on very small scales. Resolving those velocities gives a direct measurement. Another approach is looking for the telltale signatures of accretion. X-ray emission with specific spectral properties, variability on short timescales, and compact radio cores. Tidal disruption events, luminous flares that have a characteristic light curve when a star is shredded, are badged signatures of a black hole. Nuclear star clusters can be identified by their resolved stellar populations and by lacking the accretion fingerprints. Combining these diagnostics is the way to reliably tell the two scenarios apart. We should probably also return to the question of timescales, because timing matters greatly. A black hole that grows early and violently may quench central star formation and set the galaxy on a very different path than a black hole that grows late and quietly. Similarly, the effect of a black hole's feedback depends on whether it acts during a gas-rich era or later when the galaxy is already gas-poor. So in any thought experiment about no black hole, it's important to specify when the absence mattered. If SGR-A had never formed, would the galaxy have evolved differently in the first billion years? Yes, that early phase is crucial. If a black hole formed but remained forever quiescent, the dynamics would differ from a galaxy with a violently active early black hole that faded later. Think of it like the timing of a regulator. Early throttling can prevent runaway growth and fundamentally alter structure, while late throttling mostly affects later-stage replenishment and star formation. All of this underscores that the question, what if the Milky Way had no black hole, is a family of related questions, not a single one. You have to ask which black hole, at what time, replaced by what is the galaxy's merger history, which feedback modes are active. Being precise about those choices turns an undefined thought experiment into a set of well-posed, testable scenarios. Where does that leave the implication for life? It pushes us toward probabilistic thinking. A central black hole shifts odds by changing the timing of metal production, by altering the frequency and distribution of energetic events, and by reshaping the central stellar environment. Those changes tweak where and when stable, metal-rich planetary systems are likely to form, but none of these are deterministic kill switches. The Milky Way's black hole didn't cause life on Earth, nor did it guarantee it. Rather, it took part in a long chain of processes that set the stage. Remove it, and the stage gets rearranged in ways that could either help or hinder life in particular parts of the galaxy at particular times. To make progress beyond these qualitative statements, astronomers combined several methods: detailed observations of the Milky Way and of many other galaxies, targeted searches for black holes in low-mass systems, careful simulations that vary black hole prescriptions while holding other parameters fixed, and developing new diagnostics like gravitational wave detection and precise elemental abundances across many stellar populations that provide independent constraints. The interplay of these methods is what turns the what if into here's what likely would have been different with testable predictions. One concrete thing you could imagine as an observational test. Compare metallicity distributions and age spreads in a sample of galaxies that appear to lack SMBH with the Milky Way. If galaxies without SMBH systematically show earlier, more concentrated bursts of star formation in their centers, with steeper metallicity gradients and less extended star formation histories, that would support the idea that SMBH are important regulators. Conversely, if they look similar, that would suggest other processes can compensate and produce Milky Way-like outcomes even in the absence of a central engine. Right now, the sample sizes and sensitivities are limited, but improvements in survey capabilities will sharpen these comparisons. There's another practical aspect to consider. Space missions and telescopes planned for the next decades will be pivotal. The James Webb Space Telescope and its successors can examine the early universe's black hole seeds by peering at galaxies when they were very young. Extremely large ground-based telescopes will resolve nuclear regions in more distant galaxies. Radio arrays and X-ray observatories will hunt for faint AGN signatures in dwarf galaxies. Gravitational wave observatories will map the history of black hole mergers. Each of these probes addresses a different corner of the question of black holes' roles in galaxy evolution and in the conditions for life. Finally, and this is a more human-scale thought, the fact that we can even frame this question is a tribute to how far astronomy has come. We can measure stellar orbits near the galactic center, map gamma-ray lobes that span tens of thousands of light-years, simulate entire galaxies in digital universes, and use the fossil record embedded in stellar abundances to reconstruct billions of years of history. As we collect more data and refine our models, the what-if scenarios become less speculative and more constrained, letting us say with increasing confidence not just that black holes matter, but how much and in which ways they tip the cosmic balance between barren and potentially life-friendly galactic neighborhoods. So the next set of things to look at are the detailed, testable differences one would expect in star formation histories, metallicity gradients, and transient event rates between galaxies with and without central SMBHs. Running matched simulations, improving low-mass black hole censuses, and combining electromagnetic and gravitational wave observations will progressively replace our informed guesses with quantitative assessments. Those are the projects that will take the speculation about no black hole and fold it into the precise science that tells us whether removing SGR A would have made the Milky Way a dramatically different home for planets, or only a subtly altered one. We've walked through a lot of territory so far. What Sagittarius A is, how it shapes the Milky Way's inner workings, how its outbursts can heat and displace gas, and how those effects ripple outward into star formation, chemical enrichment, and even the probability landscape for planets. The natural next step is to ask, how would we actually tell from observations and simulations whether a galaxy really lacks a central supermassive black hole, and what concrete, testable differences should we expect if that were true? That's the practical question that turns a thought experiment into science. Let's dig into the specific tests, examples, and predictions so you can see how astronomers turn what if into here's what we expect to see. First, the smoking guns. If a galaxy truly lacks a compact central black hole, certain observational signatures should be missing, and other features should be more common. The most direct fingerprint is dynamics in the very center. A compact object, a point-like mass, produces very fast stellar motions close in. We measure that by looking at the velocities of stars as you get nearer and nearer to the center. If velocities spike dramatically within a tiny radius, that's strong evidence for a central, compact mass. If the increase is gentle and the central motions stay moderate, that's what you'd expect if the mass is spread out as a dense star cluster rather than concentrated in a black hole. But dynamics isn't the only clue. Accretion, the process of material falling onto a black hole, lights up the center in characteristic ways. Even a modest black hole that occasionally feeds will produce X-rays, small-scale radio emission, and sometimes optical signatures from hot gas. We call these low-luminosity active galactic nuclei, AGNs. If a population of galaxies systematically lacks these accretion fingerprints when we expect them, that suggests either black holes are absent or they're uncommonly quiet. On the flip side, if a galaxy's nucleus is dominated by a dense, resolved star cluster rather than an unresolved point source, that's another indicator of a non-black hole central architecture. Then there are transient events. Tidal disruption events, TDEs, occur when a stray star wanders close enough to be torn apart by a supermassive black hole. The shredded material glows brightly for months to years, mostly in X-rays and ultraviolet. If you look at a galaxy sample over a long enough time and find very few TDEs compared to what you'd expect from the stellar density, that's a hint that a compact black hole may be missing. Similarly, the population of hypervelocity stars, the rare stars flung out of the galaxy at speeds of hundreds to thousands of kilometers per second, is linked to interactions with a compact central mass. A dearth of such stars, after accounting for other ejection channels, could point in the same direction. So those are the observational diagnostics. What do they predict in practice? Simulations and comparative observations let us make more concrete claims. Prediction 1. The inner structural difference. Galaxies without a central black hole are more likely to host dense nuclear star clusters. Rather than a tiny region dominated by relativistic gravity, you'll find a compact but resolved assembly of stars whose dynamics are more modest. These nuclear clusters tend to form when gas flows into the center and forms stars rather than feeding a black hole. Observationally, low-mass galaxies often show exactly this. Their nuclei are star clusters, not, in prediction 2, different star formation histories and metallicity patterns. Without black hole feedback to heat gas and launch outflows, gas can collapse more readily into stars in early, gas-rich epochs. That tends to produce more centrally concentrated early star formation in some models. The upshot is a steeper metallicity gradient, meaning the center becomes metal-rich early while the outer disk lags behind, and a shorter, more intense period of star formation that can exhaust central gas earlier. If a set of galaxies lacking central SMBH systematically shows these traits, it would strengthen the causal link. Prediction 3. Low rates of certain transients and gravitational wave signals. TDEs should be rarer. Extreme mass ratio inspirals, tiny compact objects spiraling into a big black hole and producing low-frequency gravitational waves, would be, by definition, absent. That affects the expected low-frequency gravitational wave background that instruments like LISA will measure. If the cosmic population of SMBHs were much smaller than we think, the gravitational wave sky would be quieter at those low frequencies. Prediction 4. Fewer hypervelocity stars created by the central slingshot mechanism. There are other channels for producing runaway stars, binary interactions in dense clusters, three-body encounters in star-forming regions. But the characteristic extreme speeds some hypervelocity stars carry are especially easy to generate via close passes to an SMBH. A galaxy without such a machine would have a different distribution of ejected star velocities. Those are broad predictions. Now let's make this more tangible with real examples from nearby galaxies, because nature already gives us a variety of central setups to study. M33, the Triangulum galaxy, is often pointed at as a candidate that lacks a massive central black hole or has one that's unusually small. Its nucleus is dominated by a star cluster, and efforts to detect dynamical evidence for a compact object have come up empty or with only very small limits. M33 also remains a star-forming, gas-rich galaxy, qualitatively consistent with the idea that, at lower mass scales, star formation feedback from stars dominates the regulation of gas rather than black hole feedback. NGC 4395 is a different interesting case. It's a low-mass galaxy but hosts a bona fide active nucleus, albeit a tiny one. Its black hole is much smaller than those in large galaxies but clearly present. That shows the landscape is continuous. Some dwarf galaxies have central black holes, some don't, and some have nuclear star clusters. Cases like NGC 4395 prove that black holes can exist at very low masses and that detection capability matters. Henneis 2-10 is another compelling object. A relatively small, gas-rich galaxy that appears to host an intermediate-mass black hole and, simultaneously, strong central star formation. It's a useful laboratory for understanding competition between nuclear star formation and black hole growth. Observing objects across this spectrum helps us test whether the presence or absence of a black hole is connected to other galactic properties in predictable ways. So how do astronomers gather the data to test these predictions? A multi-pronged approach is used. Dynamical measurements. Using spectroscopy and high spatial resolution imaging, astronomers measure how fast stars and gas move around the center. If velocities rise steeply within a tiny radius, that points to a compact mass. Instruments like Hubble, the Very Large Telescope, and future extremely large telescopes can do this in more galaxies and to smaller scales. Multi-wavelength surveys, X-rays from hot accreting gas, radio compact cores and jets, infrared dust-enshrouded star formation, and optical spectroscopy ionization signatures, together reveal whether a nucleus is actively accreting or dominated by stars. Time domain surveys, transients like TDEs are intrinsically variable. New, wide-field time domain observatories, the Vera C. Rubin Observatory, for example, will catch many such events across the sky and let us estimate occurrence rates. Comparing observed TDE rates with expectations from stellar densities will help constrain the fraction of galaxies lacking SMBHs. Gravitational wave detectors. LISA and pulsar timing arrays will probe the low-frequency gravitational wave background and directly detect mergers of massive black holes. If SMBH were less common or smaller, the gravitational wave imprint would differ. That's a powerful, independent probe. Stellar archaeology. By measuring the ages and element abundances of stars at different radii in many galaxies, astronomers reconstruct star formation histories and metallicity evolution. This helps test the prediction that black hole-free galaxies might show faster, more concentrated early enrichment. Those tools are already producing data, and they'll improve dramatically in the coming decades. That's important because the theoretical side, simulations, can give us predictions, but only if they are tested and calibrated against real galaxies. Let's talk about simulations briefly, because they're how we translate physical intuition into measurable predictions. When modelers run a virtual galaxy without a black hole, they have to be careful about how they set up the experiment. There are different controlled ways to do it. Replace the black hole's mass with a smoothly distributed mass in the central region, so the galaxy's total mass stays the same. That isolates dynamical differences from mass loss artifacts. Keep the mass but turn off accretion and feedback, showing what changes are due solely to the energetic role of the AGN versus the gravitational role of the mass. Remove both the mass and feedback, simulating a galaxy that never had an SMBH. Each choice produces different outcomes, which is why any no black hole claim must come with a precise definition of what was removed or altered. The consistent message from many simulation suites, Illustris, Eagle, Fire, TNG, and others, is that black hole feedback is a useful knob for reproducing the observed population of massive, quenched galaxies. Without something to limit star formation in the most massive systems, simulations produce galaxies that are too heavy with stars. For Milky Way mass galaxies, the effect is more subtle and model-dependent. Sometimes stellar feedback can take care of regulation. Sometimes you need moderate black hole episodes to match observations. That's why the Milky Way's black hole being quiet today doesn't imply irrelevance. A few episodes of activity in the right epochs can do a lot of work. We should also look at the cosmological angle. How common are galaxies without SMBHs? Astronomers call the fraction of galaxies that host a central black hole the occupation fraction. The occupation fraction is easier to measure for big galaxies. They nearly always have SMBHs. For dwarf galaxies, the census is incomplete because small black holes are faint. Current evidence suggests the occupation fraction is not 100% at lower masses. Some dwarf galaxies genuinely lack central black holes at detectable levels, and others host low-mass black holes. Measuring this occupation fraction across mass and environment is one of the key empirical goals, because it tells us about the prevalence of seed formation channels early in cosmic history. If seeds were rare, many dwarfs would lack SMBH today. If seeds were common, we'd expect most galaxies to host something at their centers. That matters for habitability questions too, because if black holes were essential for pacing star formation in many galaxies, we'd expect different statistics of planetary systems across cosmic environments. But if many galaxies evolve just fine without them, that weakens any claim that black holes are necessary for life-friendly conditions. The bottom line is this: we don't yet know how essential SMBHs are across all galaxy masses, but we have clear observational strategies to find out. Let's pivot to implications for habitability and the galactic habitable zone, because that's the most human-centered piece of the puzzle. Earlier, we sketched how black holes influence metal distribution and star formation tempo, and how that affects where Earth-like planets might form. We can refine that by considering timescales and radial dependence. If black hole feedback paces star formation, it spreads metal production over time. Metals are the raw material for rocky planets. A regulated, extended enrichment history increases the odds that planetary systems form in epochs when local radiation environments are calmer and massive star explosions nearby are less frequent. Conversely, if the center of a galaxy forms its stars early in a violent push with little regulation, you may get lots of heavy elements early, potentially enabling some early planet formation. But the aftermath could be a long, gas-poor lull with few prospects for new planets later on. Radially, a black hole that drives gas into the halo and redistributes it can enrich the outer disk relative to a no-black hole case, because ejected metals can rain back down at larger radii. That could broaden the galactic habitable zone outward. However, an overly violent AGN episode that ejects a lot of gas entirely could impoverish the galaxy and reduce the total number of planets formed overall. So the net effect of a black hole on habitability depends on the balance between gentle, mixing outflows and catastrophic, gas-cleansing winds. It's also important to remember that local factors dominate. Whether a planet can support life depends primarily on its star, its orbital stability, the planet's atmosphere and composition, and nearby energetic events like supernovae and gamma-ray bursts. The central SMBH influences those environmental statistics indirectly by changing when and where massive stars form, but it's not the single determining factor. That's why I keep describing the black hole as a probability shifter. It tilts the odds of favorable conditions across galactic scales rather than flipping a universal life switch. Now let's consider the long-term and the weird scenarios, because they illuminate how black holes influence cosmic evolution in surprising ways. One such scenario is a galaxy that forms a black hole and then loses it. Black holes can be ejected from a galactic center after a merger if the merged black hole receives a strong gravitational recoil, essentially a kick from asymmetric gravitational wave emission. A recoiling SMBH can wander, or even escape the galaxy if the kick is large enough. That's extreme but possible. A galaxy that temporarily loses its SMBH and then regrows one later would have a complicated evolutionary history. Early star formation might run unregulated for a while, then later the new black hole could start shaping the gas reservoir. Observationally, detecting a displaced active nucleus or searching for off-center AGNs helps track these events. Another interesting twist involves intermediate mass black holes, IMBHs, objects in the 100 to 100,000 solar mass range. These could live in globular clusters or dwarf galaxies and potentially seed a larger SMBH later on. If a galaxy lacks a central SMBH but hosts IMBHs wandering in its halo or nucleus, they could still contribute to some dynamical and energetic phenomena, albeit at much smaller scales. Those IMBHs can produce X-ray flares, merge and produce smaller gravitational wave events, and even perturb local stellar dynamics. So no SMBH doesn't mean no compact object drama. The spectrum of black hole masses matters. We also should mention cosmic rays and their potential planetary effects. AGNs accelerate particles to very high energies, which can propagate through the galaxy. The galactic cosmic ray environment is mostly governed by supernovae in the disk, but central AGN episodes can enhance the flux of high-energy particles in the inner regions. For planets close to the center, that could alter atmospheres in ways that matter for habitability. For the Sun at its present position, SGR-A's historical activity has not been intense enough to pose a clear danger. But for stars sitting a few thousand parsecs closer to the center, historical AGN flares could have been astrophysically significant. So the absence of a central SMBH would make the inner galaxy consistently calmer in that specific sense, at least regarding AGN-sourced cosmic rays. Let's bring up a concrete, near-future observational test that ties many of these threads together. Imagine a survey selecting a large sample of Milky Way-like galaxies by mass and environment, and then classifying their central regions into 3 bins. Clear SMBH dynamical or accretion evidence, nuclear star cluster without SMBH evidence and ambiguous. For each bin, measure the radial metallicity gradient, the central star formation history, the TDE rate, the hypervelocity star production rate, and the galaxy's recent outflow history via absorption line studies of halo gas. If the SMBH bin shows systematically flatter metallicity gradients, earlier quenched central star formation, higher TDE rates, and more energetic outflows, while the nuclear cluster bin shows steeper gradients and more centrally concentrated early star formation, then we'd have strong empirical support that SMBHs materially alter galactic evolution. That kind of multi-observatory, multi-wavelength program is exactly what big surveys and coordinated follow-ups can achieve in the next decade. On the theoretical side, simulations should run matched-pair experiments. Identical initial conditions, one with a realistic black hole and feedback model, one without, and a suite of intermediate prescriptions. That would quantify, for a given galaxy mass and merger history, how sensitive the end state is to the central engine. When those simulation predictions are mapped onto the observational diagnostics I just listed, you get testable hypotheses. One more important observational lever is time-domain astrophysics. Because galaxies evolve over billions of years, and we can only observe them at one moment, looking at populations across cosmic time helps us infer trends. JWST peering into the early universe is already revealing how early galaxies and their central engines behaved. If JWST shows that many small galaxies at high redshift already host growing black holes, that hints at an efficient seeding mechanism and suggests most present-day galaxies should host central black holes. If instead black hole growth looks rare or strongly tied to environment, then a non-negligible fraction of nearby galaxies might never have developed significant central black holes. Let's not skip the future of the Milky Way specifically. In about 4–5 billion years, the Milky Way and Andromeda will merge. Their central black holes, our quiet SGR-A and Andromeda's much larger black hole, will interact, form a binary, and likely merge. That will almost certainly trigger an active phase. Gas funneled into the nucleus during the merger can feed the black holes and ignite a bright AGN. The strength and duration of that AGN will shape the post-merger galaxy's star formation and structural outcome. If the Milky Way had no SMBH at that time, the merger dynamics would be quite different. You might get a massive nuclear starburst with a dense cluster forming in the center rather than a quasar phase. So the presence of a black hole today affects not just our past, but our future galactic destiny. It's also worth highlighting the difference between causation and correlation in this context. Observationally, black hole mass correlates with bulge properties, the M-sigma relation, for example. That's a powerful hint that black holes and bulges evolve together, but correlations don't prove black holes control everything. They can also arise if both bulges and black holes respond to the same external drivers, mergers, inflows, and the overall gravitational growth of the halo. Disentangling direct causal pathways from shared causes is the challenge. Carefully designed simulations and observational tests that isolate single variables help resolve causation, especially when matched across cosmological time. A final, slightly philosophical point. asking, what if the Milky Way had no black hole, is useful not just because it's a dramatic image, but because it forces clarity in how we reason about complex, interacting systems. In the real universe, you can't surgically remove a massive object and keep everything else identical. The system re-equilibrates. That's why the notion of undefined, we addressed earlier, is so important. If a thought experiment doesn't specify how mass and energy are adjusted, the question becomes ill-posed. Observers and modelers respond by crafting well-defined alternatives. Redistribute the mass, turn off the feedback, or banish both mass and energy, and then follow the consequences. Those are the concrete scenarios we can test. So where does the current state of knowledge leave us? The lived answer is: black holes matter, but the degree and ways they matter vary with galaxy mass, history, and environment. For massive galaxies, AGN feedback is almost certainly central to producing the quench population we see. For Milky Way-class galaxies, the effects are important but subtle and epoch-dependent. A few episodes of activity can significantly influence gas flows and enrichment, but much of the disk's long-term structure and the Sun's local neighborhood are governed by larger-scale mass distributions and local star formation processes. For dwarf galaxies, stellar feedback often dominates, and black holes, if present, are generally smaller players, though they're still interesting for the special effects they can produce. If you want a short checklist of observable differences we'd expect in galaxies truly lacking central SMBHs, they'd be: prevalence of nuclear star clusters instead of compact AGNs, steeper early metallicity gradients, lower TDE rates, fewer SMBH-driven outflows in the halo, and differences in hypervelocity star statistics. Probing these markers across galaxy samples of different masses and epochs is exactly what current and future observational campaigns aim to do. The exciting part is that the coming decade will bring a flood of data that touches every piece of this puzzle. JWST is probing the earliest black hole seeds. Extremely large telescopes will resolve stellar motions in more distant nuclei. The Vera Rubin Observatory will revolutionize time domain surveys and provide robust TDE statistics. LISA and advanced pulsar timing arrays will open a low-frequency gravitational wave window into SMBH mergers. Radio telescopes and X-ray observatories will push the census of low-luminosity AGNs in dwarf galaxies. Together, these facilities will let us map the occupation fraction of black holes across cosmic time, measure how feedback redistributes metals and gas, and quantify how central engines shift the odds for planet-forming environments. In short, the question, what if the Milky Way had no black hole, is no longer merely a playful thought experiment. It's a set of precise, testable alternatives about the structure, history, and future of our galaxy and of galaxies in general. By combining dynamics, multi-wavelength observations, time domain studies, stellar archaeology, and gravitational wave astronomy, we'll be able to say with increasing confidence how often galaxies forego central black holes, what difference that makes for their evolution, and how much that difference matters for the odds of planet formation and life. Meanwhile, for now, the Milky Way carries its quiet giant, SGR-A, whose occasional cycles of activity have nudged our galaxy's history but have not dominated the full story. Watching how astronomers untangle those nudges from other actors will be one of the most interesting scientific dramas of our time.